Good day, everyone. I'm Maling Pereira, and I'm going to introduce you to HMAP, a machine learning agent that performs physical database design tuning. And I'm going to show you a glimpse of the huge potential of Bandit technologies have in the area of database physical design. In very simple terms, physical design tools try to answer the question of what is the best physical database design for a given workload. And the design tools have to consider some physical constraints like memory limits when answering this question. If you take a closer look at the PDS tuning process in practice, normally a DBA provides a representative workload for the physical design tool, which I will refer to as PD tool. And the PD tool will answer with a recommended set of physical design structures. In short, we call it a PDS configuration. Internally, PD tool uses a query optimizer, cost model to do a what if analysis. In this what if analysis, PD tool proposes a PDF configuration and the optimizer provides an estimated benefit. This process happens again and again for a large number of configurations, which will allow the PD tool to pick the best configuration based on the estimations. However, there are two main problems in this setup. First, the estimated benefit is unreliable, mainly due to the gaps in the cost model. Secondly, the seamlessly innocent step of representative workload selection. While it was not very hard in the past, with modern applications with dynamic workloads, it is not trivial. To further understand this problem, let's take a close look at the example of suboptimal access path choice. This example shows an access path chosen by the optimizer for a query that joins two tables. Optimizers have chosen a nested loop join as a join operation. As you might already know, in a nested loop join, for each tuple we get from the outer relation, we need to do a lookup in the inner relation. Therefore, this is used when we have small number of rows from the outer relation. With an estimation of 6,000 rows, optimizer picks the nested loop join. However, in this case, table returns 108,000 rows. A nested loop join with large number of outer relation rows can quickly lead to performance regressions. Unfortunately, these issues can be found even in state-of-the-art index tuning tools. This has been demonstrated again and again in previous papers as well as in our papers. If we actually create a PDS rather than hypothetically and observe the query returning times, we can have a better measures than completely relying on statistics. However, we are talking about a massive action space. Almost every combination, permutation of columns in the database can be turned into a valid physical design structure. Therefore, trying to create or materialize each physical design structure is clearly not practical, especially with the high creation costs from rich physical design structures like materialized fifs. This is impossible. So let's get ourselves familiar with multi-arm bandits because that's what we are going to use with HMAP. Getting its name from array of slot machines, bandits is wrapped around the simple idea of pulling one arm and these arms observe its reward. The catch is we can only observe the reward for the arms played by the bandit and not the others. With this limitation, there is always a trade-off of exploration and exploitation. Whether to stick with the best arm based on the previous results, or to try an undexplored arm to get more information about it. So ultimately, the target of the bandit is to find the sequence of arms to maximize the cumulative reward. What I explained is the basic map problem. There are many map variants as well. What we are interested is in the contextual and combinatorial UCB bandit variant, which in short known as the C-squared UCB. To understand why this variant is important to us, we need to understand three main concepts of C-squared UCB. C-squared UCB guarantees to converge to an optimal policy. C2UCB allows the use of context for each arm, providing additional information about the arm and the environment that the learner can observe before taking a decision. What really fascinates us is that given enough rounds, context allows the bandit to predict the reward of the new arm at the first sight without trying it even once. As you can understand, this property is very critical to make our solution practical even in large databases. Finally, the combinatorial property allows the bandit to pull multiple arms in a single round under a given constraint. Most importantly, C2UCB comes with a worst-case safety guarantee, which is hardly found in other general reinforcement learning techniques. I don't think we can move forward explaining HMAP without mentioning DBA bandits, one of our previous works. DBA bandits introduced bandit-based solution for index tuning. It showed superiority over state-of-the-art commercial tuning tool and general reinforcement learning approaches. And it demonstrated strong performance against dynamic workload as well as skewed datasets. However, it only worked in the limited action space of index tuning. Our attempts to extend DBA bandit to tune multiple index structures, specifically indices and materialized views, was not very successful. Addition of materialized views complicated the design of arms, context, as well as reward. We understood this design is not very scalable. Furthermore, the increase in action space and the high creation cost of materialized views led to high cost of exploration. As a result, we designed HMAP architecture, which allows straightforward and customized design for individual physical design structure, at the same time considering all physical design structures holistically as well. Unlike DBA bandits, HMAP tries to get the best of both worlds by using optimizer knowledge as well as actual execution statistics. However, I like to be very clear that we are not using optimizer cost estimates for our predictions or in our bandit arm context or reward design. We use hypothetical checks to make sure recommended physical design structures will be at least considered by the optimizer before creating it. We are not interested in learning what the optimizer thinks the best option is, but rather we are interested to know if the optimizer thinks our recommendation will result in a loss. Because it doesn't matter if that is right or wrong. What optimizer believes is not relevant. If optimizer believes it will result in a loss, it will not pick our recommendation, and we will not learn anything by creating that physical design structure. But if it believes it will result in a gain, then even a small one, we have a chance. We use this knowledge to cut down exploration paths, which will not be useful. These hypothetical checks helped us to reduce the creation costs by up to 58% in some cases. In HMAP architecture, we have two layers of bandits. In the first layer, you will find large number of small bandits that work in the small action spaces. These bandits can have customized context that will provide better accuracy in restricted domains. In our implementation, we have created one bandit for each table in the database and one more to tune materialized views for the whole database. However, HMAP framework is flexible to use with a different setup. For example, you can go with grouped tables for each bandit. L2 bandit uses recommendation provided by L1 bandit as arms and selects the best PDS configuration based on those arms. Configuration flows from left to right, whereas the reward that we get from creating those configuration will be backtracked into L1 bandit via the L2 bandit. So let's further understand this using an example. In the top left corner, we can see a new query coming in, and the bandit observe that to understand the predicates as well as its payload. And it notices the running time of this query before tuning. Based on the predicates and the payload, L1 Bandit creates arms representing all possible physical design structures using these 3 columns. In this case, we will have arms for Bandit tuning for table X as well as MV Bandit. And other table bandits will not have any arms right now. In this example, L1 bandit relevant to table X recommends index 1 and index 2, and the MV bandit recommends MV1 and MV2. These recommendations become the arms for level 2 bandit. Based on the current knowledge and the experience, L2 bandit picks 1 or more arms for materialization. For the sake of simplicity, let's assume bandit picks 1 arm based on the memory budget. Here the MV2 arm is materialized after the hypothetical check. When the same query returns, Bandit will again observe the performance after tuning. And in this example, Bandit observes 10-second gain in execution time. And at the same time, Bandit is mindful about the creation cost of the index as well as its memory consumption. This reward gets distributed to relevant bandits. In this case, it would be the L2 bandit and the MV bandit. Exact reward computation and the backtracking is a bit complex and this than what I explained. And I encourage all of you to read the paper for more information. It's worth noting that HMAP can handle new table additions in the runtime. It will simply add more L1 bandits based on the observations. Our system is thoroughly tested using 4 publicly available well-known benchmarks. In the y-axis, you can see the total workload time, which includes index recommendation time, index creation time, and query execution time. And the first graph talks about repetitive workloads that you normally see in reporting applications. And in the second graph, you can see totally ad hoc workloads, which are totally randomly selected, which shows more random environments like cloud operations. As you can see, MAP performs much better than PDTool under most of these benchmarks in both settings, except for TCP/H. Especially note that under skewed datasets and complex workloads, MAP performs exceptionally well. From this, we are clear that HMAP is doing better than 2 baselines in total workload time. But to understand the quality of recommendations, we need to drill down to the execution times of the queries. To further understand this experiment, this graph shows the execution time per round for each tool. While the total workload time for PDTool was higher than the noindex due to high recommendation times, we can see that PDTool is doing much better than noindex when we only consider the execution time. Still, HMAP performs much better than the PDTool. We can see large spike from PDTool in few points due to wrong access path selection, impacting the running time of some TCP/H query 22 instances. Best thing about HMAP is its flexibility. You can change the scope even in the runtime. Here we have used HMAP to work only in the index action space so that we can test it against best and well-known index tuners. And this comparison include well-known Microsoft AutoAdmin, Anytime, and relaxation algorithms, PostgreSQL Dexter, DB2Advice, and our own predecessor, DBA Bandits, marked as DBAB. And it shows 19.5% better total workload time compared to the second best option. To conclude, I like to summarize the presentation in 4 key points. HMAP is a lightweight map solution for physical database design tuning. HMAP is a first-learned solution to work in the combined action space of indices and views. And HMAP architecture is created in a way you can extend it to many more physical design structures as well. HMAP provides a search method that combines the optimizer knowledge and actual execution statistics to make better recommendations and cut down on PDS creation times. HMAP provides up to 40% and 70% average improvement for integrated view and index tuning under static and random settings compared to state-of-the-art commercial tuning tool. With special thanks to my co-authors, Bastian, Ben, and Renata, I will end this talk. Cheers.